So today we are going to be looking at the second example for dynamic programming, which is longest common subsequence. So as the name suggests, you are given two sequences. It can be sequences of integers or characters. Generally we take strings, but it can also be integer sequences. You have to find the longest subsequence of characters which is common to both sequences, and by common we mean they should occur in the same relative order in both sequences, although it does not have to be continuous. So for example, if you take algorithm and logarithm, the longest common subsequence would be LGRITHM. So you can notice that it is not a continuous set of characters. So if you look at the first string, there is an LG, there's O followed by RITHM, and here also there's LOGA. So it's not a continuous set of characters, but the longest subsequence which is common or which occurs in the same order in both these sequences is this one. So that is what we mean by longest common subsequence of two sequences. It can be integer or string sequences. So this is an important problem because it has applications in a lot of domains. For the most common example being your DNA analysis. So for those of you who have some background in chemistry or biology, you will be familiar that there are 4 types of chemicals or hormones or something inside your DNA, A, T, G, C. So your DNA is made up of a sequence of these 4 entities. So to compare the similarity of two DNA entities, they check how similar these sequences are and they do something along those lines. So when you have a string of ATGC in some order, you have 2 such sequences. You want to find out the longest common subsequence. So that is one common application of this problem. So how we are going to so of course when we come to dynamic programming, like I said, it's an optimization problem which will give you a number as an answer. So the first and foremost thing to clarify here is the problem asks us to find the length of the longest common subsequence. Like your coin change problem asked you to find the minimum number of coins, here the problem is to find the length of the longest common subsequence. And then using backtracking, you found out what are the actual coins required in that example. So here you will find out what the actual subsequence is, so on. So that's that. And of course when you see longest, you know it's a maximization problem. It is also easy to note that there are overlapping subproblems here, because if you want to find the LCS of logarithm algorithm, it depends on logarithm algorithm. Like you need to find the solution to problem size n, you need the solution to problem size n minus 1, which in turn needs the solution to problem size n minus 2, and so on and so forth. So you can notice it is overlapping subproblems, which means this is perfectly an example which can be solved using dynamic programming.